Hello everyone, welcome to today's webinar, Implementing ISO GPS in your engineering team. The focus of the webinar will be to introduce GD&T and understand why more and more companies are adopting it across their engineering and manufacturing teams. But before we get started, I'd just like to remind everybody that you have just been muted for the efficiency of today's webinar, but feel free to use the chat box to ask any questions that you may have throughout. I'll endeavour to cover as many as we can at the end of today's Q&A section. So today it is our Senior Project Engineer Sam Cooper who will take us through the webinar. Sam is one of our expert GD&T trainers and has worked with a number of major industry players, spanning across various sectors from aerospace to medtech, helping them with their engineering design challenges, from improving design quality to reducing rework. So I'll hand over to you, Sam.
Thank you, Karen. So today I'm going to talk about implementing ISO GPS, or as you might sometimes see it referred to, GD&T, in your engineering team. ISO GPS is an ISO standard, and it defines geometrical product specification. It's actually a series of standards that define geometrical product specification, and there are others that define the definitions of datums and so forth. They're all very interlinked. This is very similar to the single standard for geometric dimensioning and tolerancing, GD&T, on our title slide there, which is what the American Society of Mechanical Engineers calls it. Both standards are very similar. They use substantially similar symbology and have many of the same ideas and cover many of the same topics, but there are small differences in many of the definitions between the two. So I'd always recommend referring to the relevant standard if you're doing drawings in either of them. Today I'm predominantly going to talk around ISO GPS, but I'm not going to be talking about a great deal of complexity on a technical level, so much of what I'm going to talk about would be applicable to either. So I'm going to talk about some of the challenges ISO GPS addresses, what it is, and how you can apply it in your team. This isn't a training course, but we'll talk about some of the opportunities for its use and how you can learn more about it a little later on. In particular, I'll explain what I mean by getting 57% more tolerance per tolerance. This is perhaps a slightly provocative title, but I'd like to explain and expand on that, what I mean there, a little bit later on. Excellent. So, as I said, we're going to talk about geometrical product specification, ISO GPS, some specification improvement ideas, and how one might implement that in your team. Product requirements then. As we probably know, each of our designs will have numerous regulatory, functional, or business requirements, such as some of those shown on the slide on the pie chart. No matter what sort of domain you operate in, or vertical you operate in, we all see many of these same challenges. Our design process will be complex, perhaps starting with system design, where we specify the outline of our mechanical system, parameter design, where we specify the nominal geometry of our components, what we'd love our components to be dimensionally, but something that maybe we're going to struggle to achieve in manufacturing. So we then need to consider tolerance design, where we specify the acceptable deviation of our components when we come to manufacture them from that nominal geometry. Then, once we've got that sorted, we might move on to process planning, where we start to build our manufacturing processes. The earlier we are in these stages, the more influence we have on changing our design. And I think it's important to state that for your business, these stages may well be called different things, but hopefully some of these ideas strike a chord with you. Changing key parameters after our sort of process planning stage, where we start to manufacture our components, is difficult and expensive. It really would be awesome if we got the parameters that we needed right every time. We developed our process and all of our parts came out within specification. Often it can be more challenging than that, and changes at that point can be more difficult and more expensive than they would have been if we had simply made that change earlier on and anticipated it. This is hard, but is a good goal to aim for. Changing our tolerance specifications is much the same, also challenging, potentially expensive, especially if we discover quality issues during production. This can mean that we have to look at our tolerance specification again and identify any areas where we might be able to change our tolerance specification to be able to still meet quality targets when we aren't able to meet the original specification in manufacturing. Therefore, it is key that we get our tolerance specification correct. One element of this is balancing cost and quality using tolerance analysis by considering our assembly and the functional requirements for our parts and our assembly. This is a useful technique and one we talk about in other webinars, but we're not going to discuss this in detail today. Instead, let's talk about improving our specification in order to not just talk about right first time, but achieve right first time. So let's talk about improving our specifications. We're going to start off by looking at functional dimensioning. By using ISO GPS, we can clearly communicate what is required from a part on the part drawing. For instance, we can specify that a boss must be able to be assembled to a counterpart. If we use coordinate dimensions, this is difficult to express precisely and without ambiguity, which we will explore later. What this means is that our parts will all fit together if they are created to the specification with ISO GPS. But the concept of interchangeable parts has been around since the 1880s. So our parts all fit together all the time, right? Well, maybe some of us have some amount of scrap or rework, or other manufacturing challenges. Some of this may be due to parts not being manufactured in specification or to a suitable process capability, but much of it may be down to ambiguous specifications, especially if we aren't using ISO GPS or GD&T completely or correctly. Let's look at the graphic on our slide in more detail. It describes that functional dimensioning methodology. Let us first consider the top left corner, where we have tight tolerance with poor function. So if we have tight tolerances, this is naturally going to be relatively expensive and difficult to achieve, but we're not achieving good function. This could indicate that our tolerances are allocated incorrectly, perhaps in the less important places, and we should have finer tolerances in different locations on our geometry. But this is probably where we really do not want to be, which is why it's highlighted in red. If we have a looser tolerance but also poor function, this can be okay. It depends on the quality targets for the specific item in question. So if we have loose tolerances, this is going to be relatively inexpensive to produce, but perhaps we have some costs associated with scrappage, rework, or warranty costs after the fact due to that poor function. If we achieve tight tolerance with good function, this is also okay. We're presumably producing a relatively expensive product with high quality tolerances, expensive manufacturing costs, but we're achieving a good function. So we're satisfying our customers. We probably don't have much scrap, rework, or warranty costs. So this can be okay because we're producing something expensive, but we're producing a good quality product for it. However, better still is this block here that describes loose tolerance with good function. Ideally, we want our tolerances to be as loose as they possibly can be, while still retaining good function of our device. So this allows us to both save on the manufacturing costs and also turn out a quality product at the end of the day. This is a really important concept because we don't necessarily have to use tight tolerances everywhere to do that. There are often opportunities to loosen our tolerances. And ISO GPS gives us lots of opportunities to do that. By removing ambiguities in coordinate dimensioning, we can often specify looser tolerances, but more precisely specify what it is we want from our part. This enables us to specify the loosest possible tolerance and have no impact on quality, still maintain good quality in our products. ISO GPS allows us to specify the form, orientation, location, and size of our features on our components. Regular coordinate dimensioning simply doesn't give us that level of control. By making that specification clear and detailed, we can avoid many of the costs on redesign, retooling, scrap, rework, warranty, and so forth. So, how do we implement this then? Well, we're going to start off with a very simple example just to demonstrate this idea. Here we have a red and a blue block. We have a slot and a hole in the blue block on its top surface. The first hole will be used to locate the blue part along its length. Our functional dimension, the thing we're interested in, is the flushness between the highlighted surfaces, the two on the right side. The slot does not locate our part, so this is a good example of good design practice by not over-constraining the degrees of freedom of our part. So let's look at dimensioning schemes then, and how we can use them to precisely communicate what it is that we want from our component. In this example, there are two relevant dimensions to that distance, the 200mm one plus or minus a tenth, and the 175mm plus or minus a tenth. So the total variation is 2/10 of a mil that's permissible along the length. That's between the hole, highlighted in orange, and the surface, highlighted in blue. If we look at this alternate example that uses chain dimensioning, we'll see that there are 5 relevant dimensions, the 200mm dimension along the top, and the 4 dimensions along the bottom. This means that the total permissible variation is 5/10 of a millimeter. Hopefully it's now clear why it's important to consider the function of our part when applying our dimensions. So let's outline ISO GPS. It's a symbolic language that we can use on our engineering drawings and models to define the allowable deviation of our geometry. It's an alternative to using coordinate dimensions. You can see many of the symbols that might be applicable on the slide here, but there are many others also. But it enables us to express our needs as a designer better. CAD nicely represents our perfect model without dimensional variation, our nominal geometry, but we also need to express clearly and without ambiguity what it is we need for our manufacturer, what variation is permissible. If a part is specified using ISO GPS, it shouldn't be necessary to have back and forth with our manufacturers on what processes are acceptable. For instance, you may have parts that are turned in one operation to aid with coaxiality. However, if ISO GPS is applied, you can specify exactly what you want on the drawing, including coaxiality. This is just one of the many benefits that you can learn about in our training courses and other ISO GPS content. So the benefits of using ISO GPS then. Reduced ambiguity, we have already talked about at some length, so I won't labour the point. We might reduce engineering time on resolving design issues. This can take lots and lots of time from engineers, machinists, inspectors, and so forth to resolve any ambiguous drawing issues. Using ISO GPS can substantially reduce time spent on drawing revisions to resolve this, which may be responsible for thousands of pounds worth of hours. We might also get recourse if parts are not in specification per drawing or are not interchangeable when they should be. We should end up with increased quality of our products too, a great benefit. We allow ourselves to permit intentional and functional dimensioning. So that example with the different types of coordinate dimensioning, we can take much further and consider that in 3D and align our parts, specify our parts much more precisely than we would otherwise be able to. We also might end up with good parts not being scrapped. If our specifications are incorrect, then it's plausible that we could have parts that don't meet the specification but would work perfectly well that are being scrapped. So it's really important that our specifications reflect what we actually need from our parts. So what does this look like in practice then? So if we were to compare coordinate tolerancing for the whole and ISO GPS for the whole. So we've got our coordinate tolerancing on the slide at the moment. You can see that we've got two tolerances, two dimensions in the two different directions. So what we're saying with these two tolerances is that the central axis of our hole, marked with a little red dot, can be anywhere inside this rectangle here. But then how do we decide on the tolerance zone? We consider the furthest point from the axis as the maximum misalignment of the hole. This direction on the slide, the little grey arrow I've just added. This is perhaps ineffective though, as the variation that's permissible depends on the direction of the variation. In real life, much of the time it doesn't. We just want our hole to match up with a shaft. And of course, this doesn't just apply to holes. This is a good example of the type of benefits ISO GPS can give. So what is that benefit then? So at the moment, the axis of our hole can be anywhere within this rectangle. It's worth mentioning we haven't also considered the depth of our hole into the page, which ISO GPS also specifies. But with ISO GPS, with a position tolerance, we can specify a circular tolerance zone. So we have the same variation permissible, with that little annotation there, in all directions. With that circular tolerance zone, our central axis of our hole is permitted to be anywhere in our green circle. And what that means is there are areas which would not have passed with our coordinate dimensioning, but do pass with our circle. And they still assemble together. So these parts that are in those regions, that are encased by the circle but not by the square, are parts that would have gone in the scrap bin because they don't meet the specification, but would assemble perfectly well. This area accounts for 57% more usable tolerance zone. Hence the title of this webinar. It better describes the need for a fit between a pin and a hole. This is a key benefit of ISO GPS. There are many more benefits to using ISO GPS over coordinate tolerancing too. For instance, the maximum material condition modifier allows us to specify that if a hole is bigger, more positional variation is allowed. We're essentially saying that it just needs to fit with the corresponding shaft. So in addition to the 57% more tolerance zone in the previous slide, we can also add even more permissible variation depending on the size of the hole. This is often called bonus tolerance. The potential benefits of this are huge. By specifying our parts just so they are assemblable, rather than using complex coordinate dimensions that don't express our needs well, we both improve our drawings and reduce our costs by ensuring that our parts that would have otherwise been able to be assembled aren't ending up in the scrap bin. And we can measure these types of specifications with a go, no-go gauge, as you've seen in the animation, which can be simpler and faster than some coordinate dimensioning inspections. So, let's talk about some common misconceptions then. We encounter these a lot with discussions around ISO GPS. So to begin with, the complexity. And this is potentially true. It is a new thing to learn. But the 3D geometry is complex, regardless of if it's specified or not. If it isn't specified and coordinate dimensioning is used, you're likely to introduce the ambiguity, inaccurate specifications, and cause assemblable parts to end up in the scrap bin, as I talked through. Our basics course will take approximately 1 day and will give you a good basic understanding to communicate and interpret drawing intent with ISO GPS. Suppliers aren't clear or maybe charge more. This is a key one that comes up quite regularly, but we can work with you both with courses and other tools to educate your supply chain and internal stakeholders also. It's important that everyone who works with the parts understands ISO GPS to an appropriate degree. It can take longer to specify our drawing. This is true. Certainly at the start, when we're just getting used to using ISO GPS, it may take us longer to think through. But this isn't necessarily true once we're comfortable with the standards, and it can help avoid many of the problems that we've talked about. In essence, because it provides a more complete specification, this isn't a bug, this is a feature. The final one I wanted to talk about is that ISO GPS sometimes isn't considered in BS quadruple 8. I wanted to mention that there are numerous references to ISO GPS in BS quadruple 8, the engineering drawing standard. They're referred to as BS EN ISO in various locations, and there is a small section in the newest version on some tolerance specifications. So, we've talked about some of the benefits and some of the challenges. Hopefully, you're convinced that this is a tool that you would like to be using in your engineering team. So let's talk about implementing it. I mentioned the 8 steps to implement ISO GPS at the start of the webinar when I reviewed the agenda. I'm going to review these in the remaining time for the webinar. I'm going to talk through them fairly quickly, so if you have any questions or any additional thoughts on these, do feel free to send us a message or ask a question in the question box. So my first thought on this is there are a number of steps here to implement and institute ISO GPS in your design standard and in your organization. Perhaps this webinar is step one in creating a sense of urgency, and you might look to go on to form a vision for that, enlist your SME, generate some wins with it, and start instituting that in your organization. So perhaps you're at step one. Perhaps you're a little bit further along this timeline. Regardless, do get in touch if we can support you in any way on this journey. So, we've hopefully generated a sense of urgency. We might be able to build a team to institute ISO GPS, but we might want to form a vision for what ISO GPS implementation would look like in your business. Often we find that this is converting to a more efficient process with less design loops and more quality-driven methodologies in many of the businesses we speak to. This can be a training strategy with some of our solutions, or it could be implementing other solutions as well, such as a 1D or 3D tolerance analysis solution alongside this. It can be a good opportunity to combine the two. We often find that there's benefit to enlisting a champion or SME. It's key to identify this individual to promote ISO GPS and develop the standardization of its use in your organization. Often, this person will be involved in continuous improvement and design best practice activities. It's important to enable action by removing barriers to using ISO GPS in individuals' drawings. This can often be done by implementing ISO GPS with PLM using model-based definition by specifying our dimensions on the geometry rather than on drawings. And it often goes hand in hand with digitalization and single source of the truth programs, where we want to utilize our geometry and model-based definition to ensure that our parts and our assemblies are fully specified on the geometry, and drawings are either supplementary or not used at all. We will then want to look to generating wins. So we probably want to focus on the top right-hand corner of our quadrant here, where we might have some big issues that are easy to solve with ISO GPS, quality-driven, specification-driven issues. Maybe one in your organization or associated with your role stands out to you, but if not, we're happy to have that conversation with you. It's good to start with assemblies and products with existing challenges and use these ISO GPS tools alongside tolerance analysis to identify key issues and key specifications in your parts to focus on. Finally, to sustain that acceleration, we might want to look at what a future community might look like. Often this has one subject matter expert and many users, but it might include your suppliers, partners, framework, any of the other organizations that you work with on your design. And finally, we might want to institute that with documentation. It's key that it's understood how that helps your organization succeed. Excellent. So that's a very brief overview of the 8 steps to implementation. To conclude then, I wanted to highlight some of the points we had already talked about earlier in the webinar. So let's outline some of the benefits we might see by utilizing ISO GPS. You might see reduced ambiguity in your specifications. You might be able to reduce some of your engineering time on resolving some of the issues that are associated with your specifications or other quality issues. You might, of course, see increased quality of your products, and you might see that good parts are utilized. And what I mean by that is that concept we talked about a little bit earlier, where if we used coordinate dimensioning, we might see that parts that would be perfectly assemblable might end up in the scrap bin. So we really want to be making sure that all of the parts we assemble match up with are able to be assembled, match up with our specification, such that good parts pass our inspection and bad parts do not. And it's really key that we use ISO GPS rather than coordinate tolerancing to accomplish that. And we can do this by using some of the tools that we talked about a little bit earlier. So we can utilize some of the tools from our 8 steps to enable us to achieve that. So what might next steps look like? Well, you may find below there are a number of sort of links of items that can help you. In particular, we have some demos of our courses that introduce ISO GPS in a more technical level. As I haven't done that today, that might be of interest to you. There'll be a mini series coming out with some more basic technical information on ISO GPS. And do contact us if you'd like to learn more, or if you have any specific questions, do leave them in the box. Thank you very much for your time.
Thank you very much, Sam, for taking us through today's webinar, Implementing ISO GPS in Your Engineering Team. Okay, so before we end, we've got a few minutes to move into Q&A, a chance for you to ask any questions on what Sam has covered today. If you do have a question, please feel free to write that in the question section that appears on your screen, and we'll attend to as many as we can. So Sam, we're going to move straight into the first question. I'm still concerned that GD&T is too large of a process to change and too difficult. Is there a way I can trial it?
For trialing GD&T, I would probably recommend starting it with a single program, perhaps a more simple one, and maybe communicating with any suppliers or involved parties around that and seeing how that goes. It may be necessary, as I sort of mentioned earlier, to do some education work on some elements of it to support that process, but I definitely recommend starting with a single program, something of that sort of nature. I think in one of our points in the 8 steps, we talk about setting up a vision and setting someone as a champion of it. So perhaps the champion of it could start with identifying some issues that are particular to a specific program and maybe look at making some improvements there, is probably what I'd recommend.
Thank you for that, Sam. And another question here, one that we actually get asked quite a lot. How are GD&T and tolerance analysis different?
Yes, I did mention both during the course of the webinar, I think. So GD&T or ISO GPS are our part specifications, which we talked about. They specify the variation that is permissible on a specific part, sort of in our manufacturing process, how much variation is allowed. With tolerance analysis, we want to take that variation as an input to our analysis and understand the outputs that we'll have across our assembly. So we might, for instance, have numerous parts that are assembled together, and we might want to make sure that they can be assembled together with all of the various holes and joints between them. We might want to make sure that it functions as we expect, regardless of the variation that's on the specific parts within our specification. So we want to make sure that we've accounted for the variation on our parts, using tolerance analysis, forgive me. We want to make sure that we've accounted for the variation on our parts and ensured that, considering all of our parts across our assembly, that the functions that we expect will still take place regardless of the manufacturing variation on them.
So I think we can squeeze in one more question, but it's a very good one. We already use basic GD&T, but are still having quality issues and don't use any suppliers. How do we go about fixing them?
I would probably recommend reviewing the specifications that you already have if you're still having quality issues using basic GD&T. Perhaps this is something that you might find some benefit to reviewing some educational material or reviewing the standards on and making sure that your current implementation is communicating what you want from your parts, or possibly there might be some misunderstandings in different teams or something of that sort of nature. So I think there are probably 2 main solutions, either some education for your different teams to ensure that the specifications are correctly applied, and maybe reviewing those specifications and just making sure that it's definitely doing what you think and you're happy with your application of both datums and the specifications, because they're both really important. The specifications in the feature control frames, that is, they're both really important to specifying the variation on your parts. If it's something you'd like to discuss further or have any examples, do feel free to send us a message afterward.
Brilliant. Thank you very much, Sam. Fortunately, that's all we've got time for. I'm sorry if we didn't get a chance to cover your question, but either myself or my colleague will come back to you with an answer. I hope you have found today useful and informative. Just before we go, I just want to thank Sam again. That's it, everyone. See you on the next one, but enjoy the rest of your day.